The Juno rocket is one of the Project Jupiter's entry for the Latin America Space Challenge 2021 and represents the final development of almost 2 years of quarantine. Juno's design has been in development since 2019, and its design has been constructed as an improvement of the rocket Europa, which was originally intended for LASC Cup 2020, winning 3 awards for the team in Latin America Space Challenge 2020. Juno is a 4.8 meters long rocket with a diameter of 127 millimeters. Its fuselage can be separated into 7 different parts: a carbon fiber nose cone, followed by 4 modules, a hybrid motor, and fins. In the rear section, the motor's external structure is visible, being part of the fuselage. The nose cone was optimized to minimize drag in subsonic and transonic regiment using a von Karman shape. Inside, it is the reefing cover, a device that allows the parachute to open at its full diameter by cutting a rope that keeps it reefed. Each of the tubes is hand-built using a lamination process with epoxy resin and carbon fiber. The payloads and valves are an exception, using glass fiber so that it is transparent to radio waves. The coupling is made by aluminum discs glued at each side of the tubes. The fins were also enhanced to minimize drag. They have a NACA 0012 airfoil section applied on a trapezoidal shape that gives a tube caliber stability margin to the rocket. Finally, there is a circular arc-shaped tail to minimize drag. Unlike previous rockets, which were recovered using 2 parachutes, a main and a drogue, Juno will have a single rifter quarter-spherical main parachute, as well as a pilot chute. The pilot is attached to main deployment bag, and it is used to assist in ejection. During the deployment at Apogee, the main will be reefed, meaning its diameter will be limited by a reefing line. Reefing reduced the parachute's total drag, resulting in the rocket speeds decreasing with more stability at high altitude. As the altitude decreases and the rocket reaches a predetermined level of 427 meters above ground level, a reefing cutter is activated, cutting the reefing line, and the main parachute is disreefed to achieve its total drag, greatly reducing the vertical speed until ground level. The parachute ejection system is composed of 2 CO2 cartridges that are fitted to aluminum cylinders. Beside each cylinder, there is a puncher and a small charge of black powder. At Apogee, the black powder is ignited. The punchers break each of the cartridges seals, freeing the compressed gas, which pressurizes the module. This results in the separation of the rocket's nose cone from the rest of the fuselage and ejects both main and pilot chutes at once. The ejection system was already tested many times before, including in-flight tests. The reefing system was also tested in flight with a 1-kilometer rocket Temisto, although some improvements need to be made. The electronic subsystem is responsible for detecting the correct moment to activate the ejection system and to trigger the disreefing of the parachute. Its structure is divided accordingly into those 2 individual parts. The first part is located below the parachute ejection system and takes care of the initial parachute opening. It contains 2 redundant altimeters to detect the apogee with high reliability. The primary system is a commercial off-the-shelf IRC-free altimeter, and the secondary system was developed by the team in Count with a BMP-280 barometer and a STM32 that runs an MLMS normalized least mean square adaptive filter and calculates the apogee. Both systems have already been tested in previous flights and have succeeded. The second job for the electronic subsystem is to start the main parachute disreefing. The reefing cutter is divided in 2 parts: its activation system and the cutter itself. On one hand, the activation system, which is placed inside the nose cone, contains the detection electronics in RRC-free and an SRAD detector that operates redundantly. On the other hand, the cutter itself comes with a combustion chamber through which the reefing line passes and is attached to the mains riser. The student researched and developed detector contains a BMP-280 sensor and an Arduino Nano to perform the calculations needed. Below the electronics, there is the payload module, whose structure is easily removable from the rocket. It weighs 4.5 kilograms and carries 3 major parts. First, there is a telemetry system that captures and transmits flight data, such as air pressure and GPS location. The second system is a camera, which records the flight. And finally, there is the main experiment, which is a control inverted pendulum. Its main goal is to keep a pendulum in a position perpendicular to the module's structure and, therefore, aligned to the radial symmetry axis of the rocket. The control algorithms are implemented in a microcontroller, which controls the pendulum through the use of a DC motor. Finally, it is worth mentioning that although the experiment involves movement during the flight, it's not expected to affect the rocket flight dynamics in any way. Juno's hybrid motor, named Marimbondo, is an M-class motor of paraffin and nitrous oxide and represents the final result of 4 years of development. Essentially, the engine can be divided into 4 segments: the oxidizer tank, the vent module, the valve module, and the combustion chamber. For the filling operation, we connect a hose to the valve module by means of a quick disconnect. With a command sent to the filling base, the flow of oxidizer starts into the rocket, and through the valve module, we control the direction of this flow into the tank. When the tank is full of liquid oxidizer, we have a visual confirmation through the vent module. Then, we send a command to stop the filling and stop the flow through the vent by means of a solenoid valve. In the same step, we disconnect the filling hose by the quick disconnect. With the rocket ready to launch, we send the ignition command to the launch base. It communicates with the valve module, which in turn opens the valve that was preventing the passage of oxidant and ignites the grain of solid fuel in the combustion chamber, initiating the burn. The trajectory of the rocket was simulated using RocketPy and in-house software. Juno has a predicted apogee of 3,370.8 meters, achieving it at 27.1 seconds. Its maximum velocity is 246 meters per second at approximately 0.7 Mach, and with a maximum acceleration of 7.8 gs. So that was a quick overview of Juno Project Jupiter Next rocket. Thank you for watching.